To add to what I've actually mentioned earlier, do you still remember when I was talking about getting to know the flow, getting to know what is the analysis, getting to know your issues, getting to know your solution, you verify, you validate, then the tools. I think most most of your design work is actually depending on tools where they actually verify and validate that your job is actually doing perfectly and it's efficient, and also minimize those failure whenever you take talk. I think EDA plays the biggest role in ASIC design because the amount of money that being splashed into this field is actually enormously a lot. So whenever they actually spending a lot, so they want to make sure that you be as meticulous enough to really get things done correctly. If things may deviate, even a slight 0.1% may can cause your chip to be failed. So it's important to really making sure all the flags is actually green rather than red. So in RTL, if you really think that you have done a beautiful job, there is actually a flow called lean. So this lean flow is actually important for RTL guys. So they actually run this to make sure that your RTL is doing well, and there are a lot of checks on top of that to making sure that it is synthesizable. That is most importantly. In this term of RTL, I think the whole concept here is that you want to make sure that you translate your architecture into RTL correctly, and your RTL can be synthesized later on. You don't want to write your RTL and making sure that it cannot be synthesizable. If it is cannot be synthesizable, then you can't actually have a physical blocks in the subsequent stages. So it's important for you to really know what is this tool about, and Cadence is actually using Jasper Gold, and if not mistaken, Synopsys is using Formal Verification FE. So if you really go through this, I think it could be another jobs for you. So if you really go through, as I told you, in this industry, you can actually be an initiator of from reverse engineering. So reverse engineering means you may have a basic knowledge of Verilog, and then you run lean and making sure that all those syntax, all those coding that's written in RTL could be correct. So in any of this, you would be definitely be doing really well, and things gonna go well from there onwards. So it's important for you, to really get to know what kind of tools being handling in that specific flow. Like synthesis, when you talk about synthesis, I think the most basic tools that you really need to know if it is either DC or Genus. So on top of that, to making sure that your file of those RTL, and also your gate netlist, there's no mismatches. So that's where you actually run your LEC, or if let's say there's a low power, you talk about spyglass. Spyglass is also a very interesting topic. I think if you really think that you might not actually wanted to try something more simpler, but it gives you impact. As an initiator, you can actually try to start from UPF, because in UPF, I think the amount of effort for you to start from the beginning is not that much as in RTL, because UPF you actually start with your great power domain. So you need to have your domain. Then right after having a domain, you need to have your power distribution network. Your power distribution network, it actually consists of your nets, of your ports, of your power switch. So these are the one who actually be the interface or the bridge to inside your design. Then we talk about power state table, because it is a low power design. When we talk about power state table, which are the region actually which are the islands or voltage area are gated and also ungated. From there onwards, let's say there are multiple domains. You wanted to make sure that if let's say island A or B on, and you want to see C off, or B on, C and A off. So there are actually And all these are actually being designed, drafted, documented by the architect guys. So from there onwards, you really get to know what is in power state table. Then right after that, you actually define your isolation cell, your level shifter, and your retention cell. So it's just as simple as this, but it may not be that simple. Yet you really need to know, because the thing is that you might create a top power domain, but you need to know what kind of hierarchy actually need to be in that particular island. Maybe there are only like certain hierarchy sits in there. Then right after that hierarchy should not be sitting there. I think I may look easy in terms of the content, but there are more things to talk about. Like for instance, you really need to know what is isolation. So why isolation is needed? Because you don't want your signal that is being turned off be a deterministic value. So you want a certain confirmed value, whether it's 0 or 1. As usual, we know our computer language being talking in binary language, which is only 0 or 1. So that's important for you to know what is the isolation cells about. Now, when we talk about level shifter, it's the different voltages in your design. Maybe you might want to actually have voltage from 0.7 to maybe 1.1. So this is different voltage. And retention cell is something that you want to retain the state. Just imagine you have a state of just imagine you have a final state machine that it already at the stage 2, and you don't want to actually reset. The moment you turn off, you don't want to reset to state 0. You want to retain that particular state. So that's the reason we have this retention cell. There are so many things we can actually talk about in UPF, how it actually, if let's say you're not doing a good job in synthesis, how it actually jeopardizes in your placement, or it could jeopardize your CTS as well, because the amount of buffer being added, we do not know. Are they actually adding correctly at the right hierarchy, or they are actually adding with the correct buffer cell? Because you need an always on buffer in order for you to actually connect with this multiple power domain. So that there are more things for us to actually look through if you're really working in synthesis. It's not on top of that. You wanted to make sure that your scan is actually being stitched to all the flip-flop fully 100% covered fully, so that in the future there's no problem, or maybe there is a problem arises, you can actually testing it easily. On the other hand, you have your ATPG and MBs as well, so you may wanted to actually check it out on that part as well, but I may not actually go into that and talk about that more extensively. I'm just giving you the breadth of ASIC design, how this ASIC design all about. Then right after that, maybe you can actually say it in terms of physical awareness as well. If just imagine this synthesis is synthesizable, you run it into the APR and getting sure that you get a floor plan, def out it, and then give it back to the synthesis guy. You could actually see how is your design gonna look like. What you just need is your port, your boundary, and also your cells, your macro block cells. So you can actually see it and you run your timing and check it out how it works. So all this about that, basically in synthesis you wanted to map it all your library cell to those logics and make sure that it can be actually run in PNR tools. And PNR tools is the last part, we call it. That's the reason it's a back end of design. You wanted to sign it off and send it your GDS2 to the foundry for fabrication, and that's your lithography process will move on. So coming back to here into synthesis, so I think pretty much that's all that we can talk about this. Thank you.